If we are to meet our climate goals, we need to accelerate an European hydrogen economy. And this is why we have set the ambitious target to increase Europe's annual production of green hydrogen to 10 million tons already by 2030. And this is why we have launched the European Clean Hydrogen Alliance.
This is a huge amount of hydrogen to come out in a very short span of time.
A pipeline is one of the quiet superpowers of the modern world. It can move energy day and night across hundreds of kilometers with no traffic jams and no trucks. So when people say, let's build hydrogen pipelines, it sounds like the easy part of the clean energy future. But hydrogen is not oil. Oil is a heavy liquid that likes to stay inside a pipe. Hydrogen is a tiny molecule that loves to escape. The dream is the same, energy in a pipe, but the rules of the game change the moment you switch the molecule. Here's the first twist. Even today, there are dedicated hydrogen pipelines. The US has a network, but it's limited and mostly serves big industrial users in specific areas, not homes and not most drivers. That gap between some pipelines exist and a nationwide network exists is the whole story. So why is scaling up so hard? Because hydrogen doesn't just bring one problem, it brings a stack of problems that multiply each other. And they show up in 4 places. It leaks, it weakens metals, it's hard to pack into small spaces, and it loses energy when you convert it into shippable forms. In a pipeline world, leakage is not a small detail. Leakage is the business model killer. Hydrogen molecules are so small that they can slip through tiny openings that other gases might not. Seals, valves, and joints that look fine on paper can become slow leak points in real life. And hydrogen leakage isn't only about losing product, it can also affect climate benefits. Hydrogen is not a direct greenhouse gas like CO2, but it can change atmospheric chemistry in ways that increase warming through effects on methane and ozone. That means clean hydrogen still has a weak spot, keeping it in the system. This is where the story gets uncomfortable. If you build a huge system and it leaks more than expected, you lose money and you lose some of the climate win. That doesn't mean hydrogen is bad. It means leakage control isn't optional. It's the price of entry. People hear leakage and think just tighten the bolts, but the pipeline system is not one bolt. It's thousands of kilometers of pipe, plus compressor stations, plus meters, plus connectors, plus maintenance over decades. Each small leak is a tiny tax. Add enough tiny taxes, and the dream gets expensive fast. Now we hit the scariest sounding word in the hydrogen pipeline debate: embrittlement. That means a metal can become more likely to crack. Hydrogen can enter some metals and change how they behave under stress. Not always, not everywhere, but enough that engineers treat it seriously. Think about what a pipeline does every day. It holds pressure, it heats and cools with seasons, it vibrates, it gets repaired. Over time, tiny flaws can grow. If hydrogen makes crack growth easier in certain materials and conditions, then just using the old pipe turns out to prove the old pipe is safe. This is why hydrogen pipelines have their own design rules and standards. It's not just the same natural gas playbook with a new label. Codes exist because materials, welding, testing, and safety margins can change when hydrogen is the molecule inside the steel. And here's the big conversion cost nobody puts in the headline. Even if a gas pipeline can be repurposed, the work can be serious. You may need upgrades, inspections, new compressors, new seals, and new monitoring. Repurposing can be cheaper than brand new steel in the ground, but it's not free. Hydrogen has a strange personality. By mass, it carries a lot of energy, but by volume, by how much fits inside a pipe, it's not so generous. To move a lot of hydrogen, you usually need high pressure, big pipes, or both. That changes compressor needs and overall system cost. So you compress it. But compression takes energy. It also adds more equipment, compressor stations, electricity supply, maintenance, and more possible leak points. That's not a deal breaker, it's just the reality of moving a small molecule at scale. This is why early hydrogen plans focus on clusters, make hydrogen near where it's used, like steel plants, refineries, and chemical sites. Shorter distances mean fewer chances to leak, fewer permits, and fewer unknowns in old pipe networks. And now we reach the fork in the road. If you can't move enough hydrogen cheaply as a gas over long distances, you start looking for other forms that are easier to ship. That's where liquid hydrogen and ammonia walk onto the stage. Liquid hydrogen sounds simple. Chill it until it becomes a liquid, then ship it like a fuel. But hydrogen only becomes liquid at extremely low temperatures. Its normal boiling point is about 20.3 Kelvin, which is about negative 252.9 degrees Celsius. That is not cold. That is almost outer space cold.
That extreme cold creates a chain reaction of costs. You need special tanks, you need insulation, you need careful handling, and you need to accept a hard fact. When something is that cold, heat always wants to leak in, so liquid hydrogen can slowly boil off. Then there's the energy bill for liquefaction itself. Many engineering studies put existing large-scale liquefaction electricity demand in the rough range of around 10 to 13 kilowatt-hours per kilogram of hydrogen, depending on plant design and scale. That's a big energy toll before the hydrogen even starts its trip. And even after you pay that toll, you still need a cold supply chain at the destination: storage, transfer, and either use as a liquid or warm it back into a gas. Studies also discuss boil-off losses during storage and transport as a key challenge that must be managed carefully. So liquid hydrogen can work, especially in controlled, high-value routes. But it's not a magic oil replacement. It's a cryogenic project. Every step needs precision, equipment, and money. That's why the pipeline dream often returns. Surely a pipe is easier than all this cold. Ammonia is a different kind of cheat. It's not hydrogen gas, and it's not liquid hydrogen. It's a chemical that carries hydrogen inside it. And the world already ships ammonia at a huge scale for fertilizer. That existing experience is why ammonia keeps showing up in hydrogen transport plans. Ammonia is also easier to liquefy than hydrogen. Its boiling point is about minus 33 degrees Celsius at standard pressure. Still cold, but nowhere near minus 253 degrees Celsius. That means you can move it using technologies the industry already understands much better. But ammonia brings its own price tag. If your goal is to use hydrogen, you eventually need to get the hydrogen back out. That process is often called ammonia cracking or decomposition. It takes heat, equipment, and usually a catalyst to do it efficiently. So the question becomes, where do you pay the energy cost? With liquid hydrogen, you pay a lot up front to get it cold. With ammonia, you pay to convert hydrogen into ammonia, then pay again to crack ammonia back into hydrogen if hydrogen is what you need at the end. Different toll booths, same idea. And ammonia has safety and handling concerns that are not the same as hydrogen's. That doesn't mean it can't be done. Ammonia is used every day in industry, but it does mean you're not just shipping hydrogen like oil. You're choosing a different risk and equipment profile. This is the shortcut everyone wants. What if we just mix hydrogen into the natural gas system we already have? Blending is being studied and tested, but it comes with limits. Materials, appliances, and safety rules can constrain how much hydrogen you can add in many real networks. Even if you blend by volume, the energy delivered is not the same as the volume suggests because hydrogen behaves differently than methane. So blending can be a tool in some places, but it is not automatically a simple bridge to 100% hydrogen pipelines everywhere. This is the moment the story snaps into focus. The problem isn't just building pipes. The problem is to build a whole system that is compatible end-to-end: production, compression, pipelines, storage, sensors, standards, and the machines that use the fuel. One weak link slows the whole chain. Now we reach the real question hiding under all the engineering. Who pays first? Pipelines are cheapest when they run full, but customers won't commit unless the pipeline exists, and investors don't love building empty pipelines on hope. That chicken and egg problem is why hydrogen networks grow slowly. This is why governments talk about hubs and corridors. A hub has anchor customers: steel, chemicals, shipping fuel, heavy industry, close enough to connect with shorter pipelines first. Then, if demand becomes steady, those short lines can stitch into longer ones. And this is also why leakage and embrittlement matter so much. If the early network leaks more than expected or needs expensive material upgrades, the first projects get pricier and future projects get harder to finance. Early performance sets the mood for everything that comes after. So, liquid hydrogen pipeline dream is not dead, it's just honest. It says hydrogen can help in places where electricity is hard, and then it adds, but moving hydrogen is not like moving oil. If we want the network, we have to pay for the first real one before it's convenient. And that leads to the question that decides the next decade. Will we build hydrogen networks like we build highways, publicly supported, built early, and filled later? Or will we demand proof of profit first and accept slower growth with smaller, local systems? Because in the end, the hardest part of hydrogen pipelines may not be the molecule, it may be the business plan.